So in this video, I will be talking about automatic differentiation and understanding automatic differentiation at an intuitive level, without too much math or too much complicated math and unnecessary terminology. And hopefully by the end of this, you'll have a better understanding of the basic concepts, the underlying concepts behind automatic differentiation, especially in Julia and how it works, and hopefully you should be able to exploit or take advantage of some of this knowledge in your own developments when you're writing code that's differentiable or intended to be differentiable. So first, a little bit about myself. So I'm a computational scientist at Pumasai. I'm a very soon to graduate. Pumasai is a pharmaceutical modeling and simulation company. I'm a very soon to graduate PhD student. My thesis just got examined and I got some positive reviews, so hopefully I'll be graduating very soon. I have some experience in a number of packages in Julia's ecosystem in machine learning, automatic differentiation, optimization, and linear algebra, and this is basically where I got some of this knowledge that I'm going to be hopefully sharing it with you today. And my GitHub handle is shown right here. So a little bit about Pumasai. Pumasai is a company, is a pharmaceutical modeling and simulation software and consulting company. So we develop software, we do consulting, and we have world-class teams in various with expertise in various topics and fields, ranging from pharmacometrics and the pharmaceutical side to statistics, machine learning, optimization, and high-performance computing, differential equations, systems biology, etc. And I probably missed a few topics here. And we are hiring, so our core development team, software development team, is expanding. And if you have expertise in any of these topics that I mentioned, essentially, and you're fluent in Julia programming, please reach out to us. You can send us an email on this email shown here. We are a globally remote company, so you can work from anywhere. Just bring your talents over, and we're happy to have you. So some disclaimers before I move on. In this talk, I am only a lowly applied math and computer science practitioner, and by that I mean that I'm not a theoretician by any perhaps definition of the word. And so I will not be attempting to be necessarily as theoretically fault-proof as possible. I will try to be as accessible, or try to make the knowledge here as accessible as possible, even if it comes at the cost of a little bit of perhaps theoretical cringe for some people. And so if you came here with any expectations, basically, I think you already made a mistake. I think you should just relax, enjoy the ride. You may learn a thing or two by the end of this talk, and that's really the main point here. And last but not least, if you're a category theorist, I think this talk is not for you. I will not be covering a lot of category theory. I will try to only stick to mostly math or math concepts that people are familiar with from high school, from maybe first year at university. If you have some kind of engineering or mathematically inclined degree, then you should be familiar with most of the math concepts that I'll be covering here, or all of them, hopefully. And so category theory doesn't really is not something most people get exposed to, and so it's not something I'm going to be using a lot here, or even referring to much beyond this slide. So first, differentiation. What is differentiation? It's like, this talk is about automatic differentiation. We're trying to talk about automatic differentiation packages. So first, let's talk about differentiation. So if we have a function f and it has input x and output y, and throughout this presentation, I'm going to always be putting the inputs at the right and the outputs at the left. And this will become clear why I'm doing this in the next few slides. But for now, let's just stick to that. Perhaps if you're a speaker of a right to left language, that might make more sense to you. But if you're not, then please try to get used to that, because we're going to be using that in this presentation. So f is called a function, and it basically, if it maps each input x in a set called the domain of the function to one and only one output y in its range, or in another set called the range of the function, right? So x and y could generally speaking be numbers, vectors, matrices, tensors, any arbitrary data structures. If we're talking about if we're talking about f being a programming function, then x and y could be anything. You can even have multiple inputs and multiple outputs, right? But for now, let's just think of x and y being simple vectors, like 1D arrays of numbers, and let's even fix the length to 3, right? Let's just say that x and y are both 1D arrays of length 3. So in that case, we can actually write down this matrix here that's called dy dx, or dy over dx, and this is typically known as the Jacobian matrix. And basically what it does is it just calculates all these individual derivatives of each element of y with respect to each element of x. We have one row for each y and one column for each x, and that's known as a Jacobian matrix of y with respect to x. So all of this should be stuff you're familiar with. So now let's talk about nesting functions. So if I'm going to have a bigger chain of functions here where we have an input u goes to a function g, gives us an output x, which goes into a function f to give us an output y, and then goes into a function h, which gives us an output v. So this long chain of functions, if I need to find what the rate of change of v is with respect to u, then I can basically use the so-called chain rule. This is probably something you also covered in either high school or uni, and basically what you do is you just expand out this dv divided by du as the rate of change of v with respect to y times the rate of change of y with respect to x times that of x with respect to u, right? So you're just building out this chain of operations, and each one of those elements or terms here is going to be a 3x3 matrix, assuming all of these variables here are of size 3 and just simple vectors, simple 1D arrays of size 3. So typically when you look at this, the multiplication order actually matters, and so you have two ways in order to evaluate this thing here, this dv over du, right? You can either go in forward, and by forward here I mean from the input side. So the input side is the right hand side, going from u all the way to v, so that's called forward multiplication here, right? And basically what you do is you multiply these two matrices out first. You get dy divided by du, and then you multiply it by this matrix here, which is dv divided by dy, and you get this dv over du at the end, right? So you're accumulating the derivatives or multiplying them out from the right hand side, from the input side to the output side, right? Now the other way you can do it is actually in the reverse order. So first you multiply this by that, and then you get this intermediate Jacobian here, which is dv divided by dx, and then you multiply this out by dx du, and you get this dv over du. All right, I'm going to be using dx du, dx over du, and dx divided by du interchangeably in this presentation. So they all mean the same thing as far as I'm concerned. So with that, like maybe in this case, it doesn't make a huge difference which way you multiply them out because they're all matrices of the same size. So you're doing pretty much very similar arithmetic, assuming you already have all these Jacobians, right? But in some cases, it actually makes sense to choose one over the other. So let's say we have a case where u has size 3 and v has size 1, right? So we have here less variables at the output than the input. Then in this case, which way is more efficient? Well, if you start from the right-hand side, you're going to start by a matrix of 3x3, or size 3x3, multiplied by another matrix of size 3x3. And this is going to take like an order or big O of n cubed operations. So that's like doing a matrix multiplication basically means you have to do each row by column, and that doing that for all of the rows and all the columns is typically way more expensive than doing something like, let's say, a matrix vector multiplication, right? So vector is just like one column of a matrix. Compare that to like doing a multiplication with respect to a whole matrix. So doing matrix multiplication is typically more expensive, or always more expensive than doing matrix vector multiplication, as long as the sizes are comparable. And so in this case, if we start from the right-hand side, you start with this matrix multiplication, and then at the end we multiply the result matrix by a 1x3 matrix. We can think of this as a row vector, and so we can multiply a row vector by a matrix. Now compare this to going from the left-hand side. If you start from the left-hand side, you start by a 1x3 matrix. You multiply that by a 3x3 matrix, and you get another 1x3 matrix here, right? Or another row vector. So you start with a row vector, you multiply it by matrix, you get another row vector, and then you take this whole row vector, multiply it by another matrix, and you get another row vector. So at every point, you're just multiplying a row vector by a matrix, and that's more efficient than starting from the right-hand side and actually multiplying two matrices out together, right? That's going to be way slower, especially if these numbers are not as trivial as 3, but there's something like 100 or 1,000, then this will really hurt your performance. And the side that you choose to start from will determine how fast your computation will be. Now, in the other case, or if we reverse the sizes if we have way less inputs than outputs, right? So U has a size 1 and V has a size 3 instead. Then in this case, for the same reason, it makes sense to start from the right-hand side or from the U and go all the way to V, just because at every iteration or every step, you're going to be multiplying out a matrix by a column vector here or a 3x1 matrix, and that will be more efficient compared to or than multiplying two matrices out of the same size. So this forward multiplication, which is going from U to V, is typically known as the forward mode differentiation, and then this reverse multiplication of Jacobians is typically known as the reverse mode differentiation, right? And that it's called forward mode because we're going forward from the input to the output, right? And it's called reverse because we're going backwards from the output to the input, from here, in this case, from left to right, right? So that's everything you probably need to know about nesting functions. And so the general recommendation is if you have more outputs or way more outputs than inputs, you should probably be using forward mode differentiation. And that's what we basically saw here. If the outputs here are more than the inputs, then you want to start from the input side, right? And that means forward mode. And if the inputs are greater than the outputs, or the outputs are less than the inputs, then you want to start from the outputs. You always want to start from the lesser side, essentially, or the lower number. And that is basically reverse mode, right? So that's kind of the general recommendation. However, it is really not that simple, and it does depend on a lot of other factors. So take this slightly more complicated case where we have four different functions here, and there is one catch though, which is that the variable y in the middle is just a vector of length 1, right? It's just a number, let's say. And so in this case, or vector of length 1, just to make everything vectors. So in this case, if you do either forward or reverse, you end up with an interesting case where at some points you have to multiply out two matrices that are 100 by 100 each, right? So let's say we go forward. So we go from U to X, that's okay. U to Y, that's fine. And then if we go from U to Z, that's still fine. That's just an outer product of two vectors, like a column vector and a row vector. But then here you end up with a 100 by 100 matrix, and you have to multiply it out by dv dz, right? And that's another 100 by 100 matrix. And so that's very expensive. Now, if you go the other way around, you also end up at some point with a matrix that's 100 by 100, and you're multiplying it with another 100 by 100 matrix, right? And so both of these are not really the most efficient way to do this computation. Now, if we try something a little bit more clever, and by that I mean if we use forward mode for some of the function and then use reverse mode for the other part of the function, then we can end up with something that carefully avoids this matrix multiplication, right? So we accumulate derivatives for this part with a certain 80 mode or a certain differentiation mode, and then we use another differentiation mode for this part, and then we combine them at the end or multiply them at the end, right? And that's something slightly less obvious than just using one mode or the other, right? And so typically, like the choice of how you can combine or which mode of differentiation to use and which one is more efficient, or how to even combine them to build something that's even more efficient than using either of them alone, that can be very much problem specific and function specific, right? Now, this whole problem of determining the order in which you want to multiply out matrices such that like you save the most computation is a well-known problem in math and computer science, known as the matrix chain multiplication problem, right? And so it basically assumes that we have all these matrices, and now we're just trying to figure out what is the best order to multiply them out in order to get the best computational efficiency, right? And there's well-known algorithms for this. And so this is probably useful to think about. Like it's useful to think about differentiation like this in terms of just a simple matrix chain multiplication. However, in practice, automatic differentiation or differentiation is even more complicated than that, because typically we don't even have this full Jacobian. Right. So if you have the matrices, yes, you can use matrix chain multiplication to analyze the best way to multiply this out. But typically we don't even have these Jacobians, and obtaining them is actually expensive. And all we really need is a way to multiply them out either from the left or the right by something. So if you notice here, all we're doing is multiplying the Jacobian by something from to the right or something to the left, right? Each Jacobian is basically that's what we're doing with it. And if that's all you really need from your function, then like you don't really need to get the full Jacobian, and I'm going to come to examples later where this is actually, it's more efficient to not have to get the full Jacobian. And often this operation of multiplying the Jacobian by something from the right or the left can very much depend, or the computational efficiency of this will depend on the function itself, and will depend on the structure of the function, the way it's implemented, and a lot of other things. And so you really, it's very hard to come up with a single kind of strategy to analyze all of these things. And coming up with the optimal way to propagate derivatives is actually a very complicated problem, and analyzing which way is the best way to propagate derivatives is a complicated problem, and can be very problem and even implementation specific. Like if you implement the same function in two different ways, you might make it like the performance can be significantly different. And we're coming to also why this is the case in the next few slides. So I guess the takeaway here is that differentiation is complicated, and so sometimes benchmarking is boss. You just benchmark everything, all the options. You try different things and see what works best. If it's not immediately obvious with intuition, or with some of the intuition that you're going to develop in this talk, if it's not immediately obvious which way to go, then just try both and see what the benchmarks tell you. So, so far we've been talking about differentiation, but this talk is really about automatic differentiation. So what is automatic differentiation? Well, it's just a way to automate differentiation, right? So you're just building this chain of functions, propagating derivatives either up or down from the inputs to the outputs, or from the outputs to the inputs, right? And so there's forward mode AD, which just uses this forward mode multiplication, or forward mode differentiation, or this so-called, I'm going to call it forward accumulation, which might piss off some theoreticians, but basically we're just accumulating derivatives forward. That's how I like to think of it, right? Going from u or du dx to dy du, and then going from dy du to dv du, right? So we're just accumulating derivatives, almost like we're adding them, but we're actually multiplying them by each other here. And same thing we can be doing is accumulating it from the opposite side, from the output side, or the reverse side, right? And or in the reverse order. And so here we can start with dv dy, then go to dv dx, and then go to dv du, right, by just multiplying out all these matrices. And so automatic differentiation is just a way to automate this. And a lot of, like in Julia, we have a lot of AD systems. I'm going to call it AD from now on. So there's a lot of AD, like different AD packages and different AD systems that can help you differentiate your function. And it could be a very nasty nested function with a lot of loops and things that you really don't want to derive its derivative by hand, but hopefully AD should help you get accurate and also efficient derivatives without having to write things out by hand most of the time. So forward mode AD is again, as I said, it just uses this forward accumulation concept, and it's generally much easier to implement compared to something like reverse mode AD. And the reason for this is because everything in forward mode AD follows the natural execution of functions. So when we're accumulating these derivatives, we're first starting with u, and then we have what we evaluate dx du, and then we multiply it out by dy dx, so we evaluate y and x, and then we multiply this out and we get dy du. And the key here is that once we actually evaluate x and dx du, we can go ahead and forget about u. Right? We don't need u anymore. And then once we compute y and dy du, we can go ahead and forget about x and dx du. We don't need any of this previous information anymore. So at any one point, we just need the output of like the output of everything that happened so far, and also the accumulated derivative or Jacobian, right? But we don't really need to store any of the history or the values that we used before, like u, dx, du. All of that can be forgotten, and that basically makes it really easy to implement, because everything just follows the natural order of execution of the functions. All you need to do is just be able to save this additional information as you're propagating your input towards your output, right? But you don't need to do much else. Just have a way to save this additional information. And that's why some people implement a forward mode AD using some kind of extended algebra, where you have just additional information stored there, and you have some rules to like you're defining all the functions for like the arithmetic functions, addition, multiplication, etc., such that the derivatives get propagated correctly, right? But the idea here is, like, ignoring all these details, the idea here again is that you can easily forget about everything that happened in the past and just remember what's happening right now, and that's really convenient when you're trying to implement these things, right? Now compare that to something like reverse mode AD, where we're starting from U, and then we like in natural order of execution, you go from U to X, X to Y, Y to V, right? But the derivatives or the Jacobians are accumulated in the reverse order. So we go from dV dy, dy dx, and then dx du. And in order to evaluate these things or these Jacobians or multiply them by something from the left, you actually need to have a lot of these intermediate values. So we need to be able to save x and y and all these different intermediate values are actually necessary and needed for the computation of these Jacobians as we're going backwards. And that's really the fundamental challenge here, is that we can't just forget about what happened, right? We need a way to go from the inputs towards the outputs, save all the intermediate values, and then have a way to propagate these, like the derivatives backward or in reverse from the outputs towards the input. And that means we have to save a lot of intermediate values. And this makes reverse mode AD much more memory intensive and much more complicated to implement and optimize in practice. And so even like in some cases where it might make sense, or in theory, let's say forward mode and reverse mode might be equally efficient asymptotically, but forward mode will probably be much faster, especially if you have like small problems, just because of this overhead that comes along with having to save a lot of intermediate values and somehow do all this bookkeeping of which functions depend on which other functions, etc. And you have to do it in a way such that you can propagate this information backwards, or traverse this information chain backwards, right? This dependence chain. So reverse mode AD is quite the pain to implement a lot of the time. And in Julia, we have a lot of different implementations with different trade-offs and design decisions. And like there's a lot of, perhaps this is worthy of a whole other talk on different trade-offs between all these different packages and how to use them effectively. But essentially the way that you can think about it is that all of them just have different ways to do the bookkeeping and do this traversing of the chain in forward and in reverse. Cool. So, but even with that, like reverse mode is useful as we covered earlier. So in some cases here it actually makes sense to use reverse mode if you have less outputs than inputs. And this is, for example, the case in a lot of machine learning applications and a lot of computational science applications. We typically have way more inputs than outputs. And so in that case, it makes sense to use reverse mode AD, even though it's such a pain to implement, but it will still be faster in a lot of applications if you do it right. So moving on, so far we've been talking about basically u and v being vectors of length 3, let's say. However, there's another viewpoint that's actually really useful and used in the implementation of automatic differentiation. And this view, I'm going to call it the one variable at a time view. So in forward mode, let's say we have our a vector ui here, or our vector u, and instead of treating or considering all of u at once, let's just consider a single element of u, right? This ui here, where I is like 1 or 2 or 3. And so if we start from just a single value of u, or a single innermost variable, so I'm going to call this the innermost variable here, and I'm going to call v the outermost variable. Right? So if we started from a single innermost variable or a single input ui, then this here becomes essentially a 3x1 column vector, and then you're propagating this forward, and so you're multiplying a 3x3 matrix here by this 3x1 column vector or matrix, and this is just a matrix vector multiplication, right, or a Jacobian. So we're taking the Jacobian of this function here, the function with input x and output y, and we multiply it by some vector, right, and then we get another vector, which is dy dui, and then we multiply dv dy, which is another Jacobian, a matrix of the Jacobian of the function that takes input y and returns output v, and we multiply this by a column vector here, which is dy dui, and we get another column vector. So at any one point, we're actually working in terms of just column vectors and basically Jacobian, the Jacobian vector multiplication here, right? So this is Jacobian of some function, and we're multiplying it by a vector. Now, if we take the reverse mode, and we take, again, just one variable at a time, but from the output side. So we're considering only a single outermost variable vi, and then we try to get the Jacobian dvi du, then this is going to be a 1x3 row vector, right? So this here, if y is of length 3, then this Jacobian here is a 1x3 matrix, or a 1x3 row vector, and we're multiplying it by the Jacobian of a function here, the function that takes input x and gives output y, and this is just a row vector times Jacobian, right? And then we get another row vector as the output, and then we multiply it by another Jacobian, and we get another row vector, etc. And so the fundamental operation here that we're using is this row vector multiplied by a Jacobian, right? So at any one point, all we're really doing here is just multiplying out a row vector by a Jacobian matrix, and that's really it's like that's a key point to keep in mind. And essentially these two these two equations here show you the fundamental operations that you need to define for any function in your chain. So if you have if you're trying to define a function such that it's compatible with automatic differentiation, or it's treated by automatic differentiation as a black box or as a primitive function, and I'm calling a primitive function as any function that automatic differentiation will not try to look into or look inside, and it's just going to be like taking some kind of basic rule that you define for this function. So every function in the chain should have a way to multiply out the Jacobian by a vector if you're using forward mode 80, or a way to multiply out a row vector by the Jacobian if you're using reverse mode 80, right? And that's just by virtue of trying to compute this in forward mode and then trying to compute this in reverse mode. You notice that really the only function that we need is a way to multiply a Jacobian by a vector or multiply a row vector by a Jacobian. So if we have a way to do this for every single function in the chain, then we're good to go. We can actually implement an automatic differentiation or like the automatic differentiation system should not need anything else from us, right? Or from the function. That's all it really needs, from the function. So moving on, so the treatment of one variable at a time actually gives us another advantage, and I'm calling it here a representational advantage. And basically, if you consider the intermediate values dx by dui and dy by dui and dv by dui, these essentially are just derivatives or Jacobians of some vector by a single number here, or a single variable here. And so this is a 3 by 1, this is a 3 by 1, and this is a 3 by 1. But the key here is that, or the key thing is that this here will be the same shape as x. And this, the dy dui will be the same shape as y, and the dv dui will be the same shape as v. And so every partial intermediate, or every intermediate derivative that you compute here will have the same shape as the intermediate variable that's associated with it. And this is really useful in the future, and I'm going to come to why it's useful. But basically, when x is no longer just a vector, this is actually very convenient because it lets us define these, represent these derivatives using just a very similar data structure to x. So let's say x was not just a simple 1D array, but it's like a name tuple or a struct with two fields, right? Then dx dui can be a struct with two fields as well, right? And the field names can be the same. It doesn't have to necessarily be the same struct. It can be a different struct, but it can have exactly the same field names, right? Now, if x is a dictionary, then this can also be a dictionary, right? And if x is like a name tuple, then this can also be a name tuple, etc. And so this is actually really convenient when x is no longer just a simple 3D like a vector of length 3 or length 10 or whatever, and especially if both x and u are not are not both vectors or both not vectors, then it gets really complicated to actually represent the whole dx by du if both x and u are like vectors of matrices of dictionaries, right? Representing that thing can be nasty, but representing a single the derivative with respect to a single variable is actually much easier because you can just use a very similar data structure to x in this case. Now, these intermediate derivatives here, when we're going in the forward direction, these are typically called tangents, yeah, so for each innermost variable ui, essentially, that's the derivative of all the intermediate variables with respect to each innermost variable ui, or a single innermost variable ui, and that's typically called the tangent. Now, in reverse mode 80, you get a very similar story, but instead of having the derivative of the intermediate variables with respect to an innermost input variable. Here we have the derivative of an outermost output variable here, or a single outermost variable by all the intermediate values or all the intermediate variables. And this is also going to have the same shape as the actual values that we're differentiating with respect to. So this is going to have the same shape as y, this is going to have the same shape as x, and this is going to have the same shape as u, right? And these intermediate derivatives in the backward or in the reverse direction are typically known as the cotangents. And that's again just considering a single outermost variable vi. Now, when all these vectors, or when all these variables v, x, u, y, etc., are just simple vectors or 1D arrays, one-dimensional arrays, there isn't really much of a representational advantage because you can easily expand it to become a matrix, right? You can easily like write dv by dy as a matrix, and that's actually what we started with. But when the true power of this viewpoint actually comes out when both the inputs and the outputs are not simple vectors. And in that case, let's say you're trying to differentiate or find out what changes in u is going to, like how much is v going to change if I change u slightly, right? And that's basically the rate of change or the definition of the rate of change. And so u and v can be arbitrary data structures. They don't really have to be kind of like 1D arrays. And I'm going to come to why this actually makes sense in one of the slides here. So focusing on a single variable at a time means that we can essentially effectively reason about these derivatives and propagate them and represent them in memory when we're doing automatic differentiation or when implementing automatic differentiation. And so it's really convenient to think like this. So far, we've been talking about all these chains of functions and how you actually propagate derivatives, but how do you do that? How do you actually propagate a derivative through a function? So let's say I have an input coming to me, dx by dui, and it's coming to this function here. How do I do this operation, this dy by dx multiplied by dx by dui, right? And the way you do this is by defining actually something called a chain rule or a rule, or using the chain, the differentiation rule that you studied perhaps in calculus for this function, and then defining a way to do this Jacobian vector product, right, for a specific function. And this is really what you need to do when you're like, let's say, trying to teach the automatic differentiation package about how to differentiate your function, because automatic differentiation is not magic. Somebody needs to teach it how to differentiate at least some of the primitive functions. So it can build this chain of functions for you, but at some point it's going to hit something that's so primitive that it just needs to learn how to differentiate it, like summation or multiplication or taking the difference between two things, etc. Now, if it doesn't know how to differentiate this, then it can't just work, right? Because like it will eventually hit a barrier where it just needs to learn about how to differentiate this. And so the key thing here is that you actually define what this barrier is, or you actually define what these primitive functions are, and where AD will stop and just use a rule that you provided to it, instead of trying to further look inside and further analyze this function and see what other functions it's calling and how can it actually differentiate it. And so building this chain, or once the AD system builds this chain of functions for you, it needs to be able to propagate derivatives correctly. And the way to do this is, like the way you can teach it about this is by defining these rules. And so there's the forward differentiation rule, which is again the Jacobian vector product, the Jacobian of a function multiplied by some arbitrary vector of the right size. And then there is a reverse rule, which is just taking this row vector, multiplying it by a Jacobian again of the function. So in this slide, we just mostly, again, repeat what I said earlier. So there are basically two fundamental operations needed here for each function in the chain when implementing AD, and this is the Jacobian vector product. This is typically shortened as a JVP operation, and that's just an operator that for each function in the chain you have to define if you're using forward mode AD. And basically what this operator does is, given an input vector v of the appropriate size, and I'm going to come to what that means, all you need to do is have a way to multiply out the Jacobian by this vector. And so the appropriate size in this case is basically the size of the inputs, because j here will be the size of j will be the size of the outputs of the function, or the number of outputs multiplied on the number of outputs will be the number of rows, and the number of inputs will be the number of columns. And so V here will need to have the same size as the number of inputs, and the product here will be the same size as the number of outputs, right? And that's the fundamental operation that you need to define if your function is to be treated as a primitive by a forward mode AD package. Now, this operation sometimes goes by the name pushforward operation, again, this v coming to u is basically going to be these intermediate derivatives that we're accumulating, and these are typically known as the tangents, as we said earlier. And so if we have the tangent v coming to us, we need to be able to multiply the Jacobian by this tangent to get another tangent, and that's called the push-forward operation by some people. And this is the primitive operation that any forward mode AD system is going to require from any function that is to be treated as a primitive function with a known differentiation rule. Now, similarly for reverse mode AD, you have another operation here, which is the row vector Jacobian product. Now, it's a row vector, but people just typically use the term vector Jacobian product, but you should know that this is a row vector, and that's shortened to be a VJP, and this is very similar operation, but we have V here being a row vector, and we're multiplying it out by the Jacobian, and in the implementation, this row vector coming to us from the AD will essentially be the cotangent or the accumulated derivative of a single outermost output variable Vi with respect to the outputs of the function. So let's say we're trying to propagate through this function here, then we're gonna the cotangent is gonna be basically the derivative of Vi with respect to the output of this function, and the goal is to be able to go from this to the derivative of Vi with respect to the inputs of this function. So we're kind of going backwards, propagating this cotangent backwards by going from this dvi dy to dvi dx, right? And that's really the goal, to go from the cotangent of the outputs to the cotangent of the inputs. So this operation can alternatively be looked at as a Jacobian transpose by a vector. So if we transpose everything here, then we just treat V as a column vector. Then we can assume that we have an input column vector, and then we multiply the Jacobian transpose by this vector, right? And V here once again needs to be of the appropriate size, and the appropriate size in this case is the same size as the number of outputs. Right, and that's the cotangent vector here, so it's going to be coming to us, this cotangent vector is going to be coming to us basically with the same size as the number of outputs, and then we have to find this product here, which is going to have the same size as the number of inputs. And this operation typically goes by the name the pullback operation or the adjoint operator, right? So both of these, everything in automatic differentiation has multiple names. So you can call it VJP, you can call it Jacobian transpose times a vector, you can call it pullback, you can call it adjoint, you can call it all that stuff. Now, another name for these operations in Julia in particular is like if you're trying to define these rules, these differentiation rules, for doing the Jacobian vector product or the vector Jacobian product, you're going to use a package, or there's one way to do it in Julia is to use a package called chain rules.jl. And that's a package that lets you define these rules basically independently from the automatic differentiation package or implementation. And then different AD packages then just use and reuse these rules defined in one place. And then that basically separates the rules from the implementation of AD or the AD system. And so if you have to define this in chain rules, then the name typically used for these operations in chain rules is the forward rule or F rule for the Jacobian vector product, and the reverse rule or R rule for the vector Jacobian product, right? And so that's another name that's perhaps a little Julia specific for these operations here. So the question is, who decides the chain of functions? And we touched upon this a little bit earlier, and basically the thing that decides a chain of functions is your AD package. And so if the AD package can do one thing and one thing only, it should be able to do this, like build this chain of functions for you, and then have a way to traverse it either forward or in reverse. And that's really the main job of the AD package. However, you as the user can also control the size of this chain or the length of this chain. And the way you do this is using what I mentioned earlier as a primitive function. So if you have a whole bunch of different functions in a chain, what you can do is combine some of these functions together into a single macro function and define a rule for this function. And what this is going to do is it's going to going to stop the AD system from trying to look inside this function, and it's going to just use whatever rule you provide for it. And that means you can combine a whole bunch of different nodes on your chain or functions in your chain into just a single function and squash them together into a single function. And that can actually be useful in when implementing AD and when trying to optimize your code. If you have a whole bunch of functions that seem to be like it's the bottleneck of your code, then it might make sense to actually combine them together in a single function if there is an easy enough rule that you can define. So a function with an f rule or r rule will be treated as a primitive. If a function with f rule or a forward rule is going to be treated as a primitive by a forward mode AD system, and a function with a reverse differentiation rule is going to be treated as a primitive by any reverse mode AD system. And that's really the fundamental thing to keep in mind. Now, there are different ways to define these rules for different AD packages. Typically, you would either like some of these ways are either package specific, or some of them are generic, like chain rules at JL, for example, is a generic way to define rules, and it can then be used by multiple AD packages downstream. And so that said, though, again, like the AD system is going to just trust to your rule that you define, and so this rule better be correct. And that means like it's actually really easy to make mistakes when you're defining your own rules and trying to derive your own either vector Jacobian product or Jacobian vector product for some really complicated function. And so it's always like necessary to test this rule against finite difference, right? And the really nice thing about finite difference approximations is that all you have to do, or all you need in order to do finite difference, is to be able to evaluate your function for different input values, right? And so that's like the least you can ask from your function, is to be able to evaluate it. And so finite difference is kind of the least demanding in terms of requirements from the function. And so and like it gives you a pretty good approximation a lot of the time. And so you need to be able to test your rule, test whatever derived rule that you have against finite difference to make sure that it's correct, because the AD system will not double check that for you. It will just use it and trust that it's correct. So in reverse mode AD or AD packages, a chain of operations is often actually stored in the forward pass. So when you're evaluating the function in the forward pass, going from u to v, for example, or the inputs to the outputs, the reverse mode AD package is going to also store all the operations and keep track of all the operations and all the functions that were called, what the inputs are, what the outputs are, any intermediate values that you also want to store there. And this is basically all the information that's going to be used when you're trying to propagate the derivatives backward from the output to the input. And this chain of operations is typically stored in something known as a tape in some AD packages, and this tape records basically the functions called, their outputs, and any kind of information that the might be necessary to propagate derivatives and to calculate these derivatives backward, right? Now, managing this tape actually adds significant overhead to the runtime of reverse mode AD compared to forward mode AD for some tape-based implementations. So not all implementations are tape-based implementations. Some of them are different. They use something called source-to-source transformation. But I'm not going there. That probably requires a whole talk. But like for at least tape-based implementations of AD, you still need to like managing this tape and doing all the bookkeeping for the tape is actually a complicated process, and that adds significant overhead compared to something like forward mode AD or implementing forward mode AD, which, as we said, is actually really simple to implement, right? And that's because of this, actually, the length of your chain or the length of your tape is important in reverse mode AD. And that's something you really need to keep in mind whenever you're writing code that is intended to be differentiated by a reverse mode automatic differentiation package. One thing to keep in mind is how long is your chain. If your chain is long or too long, or the length of your chain depends on some variable or some parameter that's going to be very large, then you probably need to optimize some parts of your function. Generally speaking, the less links, the less like the lower or the smaller the length of your chain is, the faster your reverse mode AD will be, generally speaking. So that's a very important thing to keep in mind, and to try to reason about how long exactly is your chain going to be, how many primitive functions are going to be called in the process in the forward pass, and that need then to be propagated or traversed in reverse order in the backward pass. So when do you actually need to define a new rule, right? That's probably the big question here. So there are a few scenarios in which you would need to define a rule for your function. I already mentioned a few of them, but let's just go through all the ones on the slide. And so one common scenario or one common case in which you would need to define a new rule is if your function calls another programming language. Now, if you're writing a Julia 80 system, or if you have a Julia 80 system, it won't typically know how to differentiate other programming languages. Like it doesn't know how to differentiate a C function or a Fortran function. And so if you're calling one of those external programming language routines as part of your Julia function, then you need to teach the 80 system what the derivative of these functions are. And that's a case where you actually need to define this. Unless your 80 system is one of those, I think like Enzyme these days might be able to differentiate across languages. I'm not sure about that, but basically most 80 packages are very much language specific, and you need to be able to teach it about any function that calls external or other languages. And there's actually a cool way to combine 80 systems from different languages by delegating the differentiation of a function from another language to the 80 package from the other language, and then defining some kind of interface between, let's say, an 80 package in Julia and an 80 package in Python, for example, letting them talk to each other. I think there's a tutorial somewhere on that in YouTube or something, but yeah, but there is technically it's possible to talk to other languages 80 systems using this rule concept. So you define a rule, and the rule basically just calls PyTorch, for example, right? And that's another thing, that like a rule here doesn't necessarily have to be something that you manually derive yourself. Sometimes a rule can be used to also redirect your differentiation to use another system. Right, so recall this mixing forward mode and reverse mode 80 can sometimes be useful. And so one way to do it is actually to define a rule, like let's say a forward rule, and inside this forward rule, you're actually using a reverse mode 80 package to compute the derivatives instead, right? Or you define a reverse rule, and inside this rule, you actually use a forward mode 80 package to compute derivatives instead. Or you use an external, an 80 package from another language to compute derivatives. And so there's all sorts of ways that you can actually play with this and have fun with it and optimize your functions. And so again, defining a rule doesn't necessarily mean you have to sit down, scratch your head, and write down rules by hand and then figure out how to define it. You can also just call other 80 systems or 80 packages to do that for you that might be more convenient and more kind of suitable for this particular function, right? So that's one scenario or one case where you might need to define a rule. Another case is if the function actually uses some Julia features that are not supported by the 80 system. Now, ideally, a Julia 80 system should support every single operation and everything you can do in Julia, right? Like it should be able to differentiate almost everything, but that's not really the world we live in. And a lot of these common packages, they have limitations in terms of what they can support or what they can differentiate. So one example here is Zygote, for example, which is a very well-known and popular reverse mode automatic differentiation package in Julia. And one of its main limitations as of December 2021 is that it does not know how to handle array mutation, right? And that's sometimes a big pain, because if you're writing your normal Julia code, often you might want to optimize it by pre-allocating memory and just mutating this array in place or this memory in place. And this kind of optimization can make your code not 80 compatible or not Zygote compatible. And that's not cool. It's annoying. And so that's another scenario in which you might want to actually define a rule in order to work around this mutation problem or this limitation of Zygote. Now, under the hood in your rule, you can still be using mutation to like get the output of the function, and then you can use mutation to propagate the derivative backward or do the Jacobian vector product, right? But at least as far as Zygote is concerned, it doesn't need to know that you're using mutation, because it doesn't need to look inside this function. It's just going to use the rule that you provided to it. Unless maybe you're trying to do higher order derivatives, then that becomes a problem, because now it's going to try to differentiate your rule, and then it can see the mutation now. Like you can no longer hide the mutation from Zygote. But yeah, so that's basically another scenario or case where you might need to define a rule for a function if you're doing something that's kind of illegal for a certain AD package, or it's not supported by an AD package. Now, another case which I also touched upon is if a function has a lot of arithmetic operations, but all of these arithmetic operations can be kind of squashed into a single macro or big function with an easy enough rule. So think of something like matrix multiplication. You can technically allow or you can write matrix multiplication as a triple loop or 3 nested loops with scalar arithmetic, where you're multiplying things together and adding things together, right? And then you can try to differentiate this, differentiate the loops and all the iterations in the loop. That's one way to do it. The other way is to try and look at the whole matrix multiplied by a whole matrix and define a rule for matrix multiplication, like a differentiation rule. And so the second one will be way faster most of the time, or almost all the time. And the reason for this, again, is that you're saving a lot of work, you're saving the AD system a lot of work. It doesn't need to do all the work now to figure out how to build this chain of functions, especially for reverse mode AD, building the chain of functions and being able to store and save all the intermediate variables and then traverse it all backwards. That can be very complicated to maintain, and it can add a lot of overhead. And as your matrix size increases, then this overhead also increases. But if you treat this whole operation as a single operation, as a single function call, then no matter how big your matrix is, it's still going to just be a single function call, right? It's still the chain of your, or the length of your chain is not going to be impacted by the size of the matrix, and that's a better design for AD performance than being differentiating in the individual scalar arithmetic operations in the matrix multiplication. So in this case, defining a rule is actually useful for performance, although it's not necessary, because it can still work without the rule. It will still try to build a tape. It will be terribly slow in some cases, but it's going to work. But in this case, for performance, defining a rule might actually make sense in order to shorten this chain of operations and decrease the overhead of managing a long tape, right? And that's another very common scenario or very common optimization where you can use these rules in order to optimize your differentiable code. Now, the last case I'm gonna talk about here, or last scenario where you might want to define your own rule, is if a function has a known efficient differentiation rule that's way more efficient than letting the AD system just naively differentiate the forward pass of the function. And this is a very vague statement, so let me be more specific. So what I mean by this is basically anything that falls under the implicit function theorem. And so some functions are actually like defined implicitly, or the output is defined implicitly in terms of the input, and oftentimes the way you compute the function value is not the same way you want to kind of traverse backwards to compute derivatives, because there's a way faster kind of, think of it like a shortcut from the output to the input that gives you the derivatives without having to go through every single operation in your forward pass, right? So if you have one of those shortcut methods, and the implicit function theorem is a perfect example of this, and I'm going to cover one example at the end of why this is useful, or how to an example of the implicit function theorem being useful for performance. But basically, like if you have one of those shortcuts where you can go from the outputs to the input without having to differentiate each single operation in your chain, then in this case it makes sense to actually define a rule, again, for performance. Okay, so far we've actually been talking about inputs and outputs and assuming that they're all kind of just vectors or 1D arrays, talking about column vectors, row vectors, etc. And this is okay if all you have to deal with is just simple 1D arrays or functions of 1D arrays. However, in practice, in programming, you may actually want to work with other data structures, either in the inputs or the outputs, or both. And so that is basically the motivation behind the slide. And so typically you'll find people use the word vector to refer to kind of a data structure that's a 1D array or an ordered list of numbers. And this is what I like to call here a programmatic vector. And there's actually a difference between what is known as a vector in mathematics, and what a programmatic vector is. So a programmatic vector is typically just a data structure that's a 1D array of usually, but not necessarily, numbers. So it can even be like in Julia, for example, a vector can be a vector of strings or other stuff, even arbitrary data structures. And so a programmatic vector is typically just a data structure that closely resembles what most people think of as a vector, associate with the word vector, right? And this can be like if it's a list of numbers, or if it's an array of numbers, and you can treat it as a column or a row vector when doing linear algebra, for example, and that's all cool and normal. But there is another type of vector that's actually much more general and perhaps a more correct identification or characterization of the word vector. And that's basically like the mathematical vector. So a mathematical vector is a very general kind of abstract concept, and it's so general, in fact, that a lot of things fall under it or underneath this categorization, and like it can be very difficult to implement because it's so general, right? And so in math, a vector is basically defined as any element of a so-called vector space, and a vector space is just a set of objects where so like you can pick two objects out of this set and then add them to each other, and you get another object in the set. Or you can take any object out of the set, multiply it by a scalar or a real number, and then you get another object in the set. And a few other assumptions, like you have to have some associativity and some like restrictions on what it means to add two things and what it means to multiply something by a scalar. But basically, if you have these two notions of addition and scaling, you get a vector space, and any element of this vector space is a vector. And so the definition of a mathematical vector does not put any kind of constraints or limitations on what you or how you can represent this vector, right? And that's what makes it so abstract that it's actually impossible to implement it without making some more assumptions. And that's why we have this other concept of a programmatic vector that's kind of the closest representation to what most people associate with the word vector, right? However, in as far as automatic differentiation is concerned, it might be helpful to think of mathematical vectors and programmatic vectors at the same time. And what I mean by that is basically many things in objects and data structures can be interpreted as mathematical vectors if you have these two notions in your head. If you have a notion of addition or summation between two objects, and you have a notion of scaling. And so whenever you're actually differentiating a variable with respect to some other variable, and this variable is some object or some data structure, then we can essentially treat this variable as a mathematical vector. And the reason for this is because whenever you're differentiating something or with respect to something, you already have a notion of difference. You have a notion of multiplying something by -1 and adding it to something else, right? You have a notion of scaling the difference by an infinitesimal step and taking that step to 0 in the limit, right, when you're calculating derivatives. And that's kind of what calculus does under the hood, or what it means in practice, right? And so doing that essentially already assumes that you have all these different operations that characterize a vector space. And so you can essentially treat the object, whatever data structure you use to represent it, as a mathematical vector, even if it's not just a simple 1D array of numbers. And one perhaps easy way to think of this is you can think of, like, let's say you have a struct of two fields, like a point with an x and y coordinates. Then you can think of it just as a vector that happens, like the vector of length 2, where the values just happen to be arranged in some other data structure, right? So that's maybe the easiest way to think of this. But you can also just think of it as a fundamental object that is a vector that belongs to a vector space in math. But if that's too abstract for you, then just think of it as it's a 1D array that happens to be arranged slightly differently in a different data structure. So this is very helpful to think about and to think in terms of this concept of a math or a mathematical vector. Now, if a function has multiple inputs and outputs, and if your function is no longer just a function that takes input vectors, arrays, and output arrays, but it takes some arbitrary number of inputs, and each input can have arbitrary data structures, then the really cool thing about this one variable at a time viewpoint that we talked about earlier is that the tangents and the cotangents will still have the same shape as essentially the inputs or the outputs in this case, respectively, right? And that's the nice convenience that comes out of this one variable at a time viewpoint is that if the input is, let's say there's let's say there's 4 inputs and each of those inputs is a different type, then that's exactly how the tangent will look like, right? It will be 4 tangents or 4 inputs or 4 elements in the tangent, and then each element is going to have a similar data structure to the corresponding input. Same thing for the cotangent with the outputs. If you have 3 outputs and each output is a different data structure, then the cotangent will also have 3 elements, and each of those elements will have a similar data structure to the corresponding element in the output. Right, and so that really gives you this notion of, or this ability to reason about propagating tangents and cotangents or derivatives with the forward rules and the reverse rules in Julia, or really any other programming language that has similar semantics to Julia, but I'm only familiar with Julia for automatic differentiation. So once again, this is the beauty of the innermost or a single innermost or outermost variable in the push forward or the pullback operations, which are the operations used to propagate tangents or derivatives forward, or cotangents or derivatives backward. Cool. So I'm done with the most of the theory, but just a couple more examples that I would like to showcase of, like, these are examples of where it makes sense to define a rule. So I'm not going to go into too much details into how to define like the syntax of defining a rule using chain rules.jl. That's perhaps something better left for the chain rules documentation. So I'm going to give a reference to that documentation at the end. But this is a nice example that I want to share with you because it's very important, but it's also very like useful and insightful, and it shows us a perfect example of when it might make sense to define a new rule for a function. So in this case, I'm trying to do something known as matrix assembly, and this is a very common operation if you're trying to solve a PDE or a partial differential equation by discretizing the field over a certain mesh or a certain number of elements, and then this discretization eventually leads you to like you want to do some kind of assembly where you have some matrix that's element specific. So for each element in your mesh or each cell in your mesh, you have a matrix that's a small matrix, and then you want to be able to assemble all these small matrices into a large matrix or a global matrix, and then each element has some degrees of freedom or corresponds to some global degrees of freedom. So in this case, I have my K1 matrix, which corresponds to the 1 and 2 degrees of freedom, and so what I want to do is be able to put K1 at this top corner here, which is the 1, 2 by 1, 2 block, and then I have my K2 matrix here, which corresponds to the 2 and 3 degrees of freedom. So I want to put it in this bottom corner to correspond to the 2, 3 by 2, 3 block, or this 2 by 2 block, but in the rows and the columns are 2 and 3, corresponding to the degrees of freedom of the element. So this is a very common operation, and again, it is one of those operations that in order to implement it efficiently in the forward pass, you actually need to pre-allocate memory and be smart about the way you're basically assembling this matrix or putting all these elements together, right? And this is fundamentally going to make life difficult if you're trying to use Zygote, for example, to differentiate this, because Zygote does not support mutation, at least as of this point. And so how do we write code that has an assembly operation that's also differentiable by Zygote? And this is really the code that's implemented in this package here, and this is courtesy of my colleague or my collaborator in this package, Yijian Huang, who wrote this code. So let's zoom in a little bit. And so we have here a function or a callable struct. So you can, in Julia, we have this concept of a callable struct, which is just a struct that has fields, but it can also be called like a function, right? And that's really convenient because I can store some really, I can store pre-allocated memory and some pre-computed values inside the struct, and then just reuse it every time I call this function. So that's a really cool way to organize your code in Julia. So we have this callable struct here, or a function with some states and like some fields and memory allocated, and then it takes an input KEs here, which is all the element matrices or all the element specific matrices, and that's just going to be a vector of matrices, right? So this is the notation in Julia for saying we have some vector of some matrix of some element T or some type T, right? And so this could be like a floating point, for example, or float 64 here, or the 64-bit floating point number. And so what we do here is just extract some fields or information from the struct, extract more information, pre-allocate some memory for the assembler, or define our assembler here using this really cool package called frule. And then here we're just iterating over all the elements of or the cells of our mesh, and then finding the degrees of freedom, the global degrees of freedom of each element, and storing these global degrees of freedom in this vector here, and then using this to assemble our matrix, or put the matrix KE here into the right place using the global degrees of freedom, and using this assembler, and using this nice assemble function from the frule package. Now this is mutating code. This is going to be mutating the matrix being assembled, which we're later going to return, and so that's not compatible with AD, and so that's something that we need to address. And so the way we address this is actually by defining the rrule. And this is the syntax for defining an rrule. So we have the rrule function here, and we have two inputs. The first input is the actual function that we're calling, and the second input is the input argument to this function, right? And the way we do this is I just call again, extract some information out, call the assembler to get the forward pass, or to get the value of k, the assembled k, and then I define this inner function. So that's just an inner function, or typically known as a closure function, or a closure. And I define this function here, and what it does is it takes the cotangents. So these are the dvi by dk, and the goal is to go from this to something that gives me the dvi dkes, or d like the rate of change of the outermost variable with respect to each of the input matrices, right? And that's just going to have the same data structure as kes, which is another vector of matrices, right? Now, there's another thing that you also need to consider, which is the derivative of, because this is a struct, because this has fields, then you can also teach the automatic differentiation about what like how to propagate the cotangent backwards to the fields of this struct, right? So you can also differentiate with respect to the fields of the function being called. And that's a really cool feature as well, because it lets you be able to then just like chain or define these functions or these callable structs in the middle of your forward pass, use them as a function, and then that still, like, all the information gets propagated backwards to the fields that were used to construct this struct to begin with. And so it all just works together. And so all the fields of the struct, you might also want to propagate the information backward. And so that's what I'm doing here. I'm defining this this thing called a tangent, and this tangent here basically has like it has fields that are the same fields that are relevant for the same fields that are used in this assemble k struct, right? So all this, we have a problem field, we have a k field, and we have a global doffs field, and I'm defining what the derivatives are. So whenever there is no derivative or it's not differentiable, then we use this no tangent. So this is like, can be used for anything that's like like an integer or a string or something like that, something that you don't really, it's not interesting to differentiate. And then I can also specify what the propagated cotangents are for some of the other ones. So here there's no tangent. I'm specifying, or I'm saying that there's no tangent for the problem, and there is a tangent for k, but there's no tangent for global doffs. And again, this is typically known as the cotangent, but here you can just use no tangent to say that there's no further information. There's nothing more to see here, right? Just don't look inside, or don't try to go backwards further. That's as good as it gets, right? And so we have this this tangent struct, or this struct tangent, that lets us define essentially what the propagated derivatives are for the fields of the struct ak, or the struct type assemble k. And then we have the second return value, which is the actual propagated derivatives with respect to kes, and this is really the more interesting one, right? So if you don't want to write this, you can just say no tangent for all of this. So you can replace all of this with no tangent, and that basically ignores anything that's inside here, right? Now that can introduce errors in your function if you're trying to differentiate with respect to one of the fields of ak. So if that's your goal, then you should not be using no tangent here. This is wrong. But if your goal is to only differentiate with respect to this argument here, then it's okay to replace this whole thing by no tangent, right? So that's kind of a partial rule, but a partial rule is only partially correct. So make sure that you only use it in the in the same way that you intended, or that was intended by the author of the rule, right? So rules don't necessarily need to be fully correct or fully complete, as long as they just do the job that's good enough most of the time. So again, over here, like if I need to differentiate with respect to or anything in the problem struct, for example, or this problem here, then that's going to be a problem, because that's going to be like the 80 system will treat this as a constant, and that's not the case, because if I'm interested in the derivative with respect to the fields of the problem and it's actually not a constant in the forward path, then that's going to be wrong. And that again highlights the importance of comparing your derivatives to finite difference always, because that's just at least like when you're implementing these things, at some point you're going to have to trust your rule enough that it's correct that you can just use it. Otherwise there's no point in implementing all of this. But at least initially when you're defining these rules, you need to compare against finite difference to make sure that you cover all the use cases that you're going to need, and make sure that all of them check out and all of them are correct compared to finite difference, because you can easily make mistakes, or perhaps miss a case or miss a scenario where there is one variable you might be interested in differentiating with respect to, and you put a no tangent here somewhere, and that basically messed up the derivatives that the automatic differentiation package is going to compute, right? So always check with finite difference. Now, the actual rule here is actually perhaps the least interesting part of this, but it's that our cotangent matrix here, or the cotangent, will have the same shape as the output. So recall always the cotangent coming to us, the delta here, which we call delta, is going to always have the same shape as the output of the function, which is k, which is the assembled matrix. And so we're trying to take back whatever, like propagate back this cotangent to the individual matrices. And so it turns out if you actually sit down and write the derivatives, and we have this full kind of layouting of why it makes sense. So if you try to derive the rules using some math and some chain rules, you'll see that basically everything you need is just to take out this partition or this block of the delta matrix for using the degrees of freedom of the element. So for each element, just find out what the degrees of freedom are, and then take the partition of the matrix that corresponds to this element, and that's going to be your cotangent for this particular element, right? So CI is just the cell index here. All right, so we iterate over all the elements with CI, we find out what the global degrees of freedom are for this element, and then we basically take a view or take a partition from the cotangent matrix to get our cotangent for the inputs. And this is everything we need to do. And this itself is mutating code, by the way, because we actually pre-allocated a vector of matrices here, and then we're just mutating each value here. And so that might be a problem if we're trying to do higher order derivatives of assembly or of PDE solvers, which might be an insane thing to do anyway. So maybe it's good that it's difficult. So in this case, all we have to do is return k, which is the assembled matrix, and return this pullback function, which we define here as an inner function, right? And so this, even though it looks a little complicated if you're not familiar with Julia, however, it is very, very close to the math that we covered earlier. And again, all we have to do is return the function value and return the pullback function that propagates the cotangents correctly. And that's all this rrule thing does here, using from the chain rules core, the JL package. And this then will be picked up by Zygote. So Zygote uses chain rules and uses all the rules defined in chain rules. And so if you're using Zygote to define a function that calls this assembler or calls this this callable struct, then it's going to be using this rule. And you can actually verify this by printing something here and seeing that it actually does print whatever you're printing, and that means that it's actually using this rule, right? And you can easily verify that the rule is being used and picked up by an 80 system. Now, other packages also use rules from chain rules. Some of them use it in a lazy fashion, like reverse diffjl. You can actually specify which rules you want to kind of borrow from chain rules and into reverse diff, but there are more limitations because reverse diff itself does not necessarily support arbitrary data structures. It only knows how to handle arrays, and so I'm not going there. Let's just say that different packages have different trade-offs, and for now I'm only giving examples using Zygote because that kind of is it's the probably the most conceptually general, or it's the one the most general 80 package that knows how to handle structs, and that's also slightly more reliable than all the other alternatives that know how to handle structs in the inputs or outputs. or arbitrary data structures in the inputs or outputs, not just stick into arrays. Anyways, so that's a really cool example where you can work around the limitation of AD or an AD system by defining an adjoint rule or a differentiation rule for your function that uses then mutation and pre-allocation, but then Zygote doesn't need to see this, and it can only look at it as a primitive function or a black box function with a known differentiation rule. Now, another example, which I also highlighted earlier, is the implicit function theorem. And so let's briefly go over what that means and why it's a good use case for defining rules. So in the implicit function theorem basically has to do with implicit functions. So what are implicit functions? Well, an implicit function is a function that's not explicit, and an explicit function is any function that you define directly, almost like if you have x squared, that's like given x, you compute x squared, that's an explicit function, like, or log of x, that's an explicit function, sine, cosine, exponential, etc. So most of these like primitive functions are actually just normal, or can be treated as normal explicit functions, where I give you an x, you just give me a y through applying a series of simple functions or operations. Now, the implicit function, though, is, let's say, like in this case, let's say y is an implicit function of x. So y is defined implicitly by some relationship that is satisfied with x. And this is a more general relationship than just saying y equals some function of x, right? So it's not an explicit function, but it's an implicit function where there is a relationship that needs to be satisfied. F of x, y equals 0, for example, right? And given x, if I give you x, you can always solve this nonlinear system of equation, find the roots, find what y is, and there's always going to be a single value of y or a unique value of y that corresponds to each value of x. And so in that sense, it is a function because for every x we have one and only value of y. And this function can be differentiable. And so in that case, the natural question to ask is, what is the derivative of this function? How can I get dy by dx? Given that x and y are defined by this coupling here, and not really through some explicit mapping or explicit function going from x to y. And so what is the adjoint or pullback or reverse rule of this function? That's probably a common question to ask. Now, one way to do it is actually thinking in terms of the forward pass. So how are you going to evaluate y to begin with? If I give you x, then you probably want to go use some Newton solver or Newton's method to solve this nonlinear system of equation. Let's say we have y here is a vector of length 3, then f of xy is going to be also a vector of length 3. So we have 3 nonlinear equations that are coupled, and we can solve for this nonlinear system to find what y is given x, right? And you can go ahead and then differentiate this iterative process. So this iterative solver that's going to find you y, you can actually directly differentiate that. And that's okay. It will actually work a lot of the time. It has limitations, it has perks, but it has some disadvantages, but it's going to work in a lot of the time, or a lot of the time. And so, but the problem with it is that you have potentially a very long chain of functions. Like you're differentiating all these intermediate steps potentially unnecessarily, as we're going to see, because there is actually a more efficient way to propagate derivatives backwards rather than just to follow in the same footsteps as the forward pass, right? So we don't need to follow the same steps that we followed forward to go back. We can actually have a shortcut, and the shortcut uses this implicit function theorem. And let's cover what the implicit function theorem is. And so if we have a function y of x that's defined implicitly by this relationship of f of x equals y, then one thing we can do is go ahead and write out the full derivative with respect to x like this. So the full derivative with respect to x is the partial with respect to x plus the partial with respect to y times dy dx. And that's going to be equal to 0 by definition of y. So because x and y are always going to be satisfying this relationship, then the derivative is always going to be 0. We can differentiate both sides and end up with 0 on the right hand side and this expression on the left hand side. And so let's take this partial to the other side of the negative, and then we can actually write a form or an expression for dy dx, and that's going to be minus of this Jacobian here, and that's a 3 by 3 matrix it should be invertible if your function is indeed a function or a unique function, and this should be invertible here. And so if it's invertible, then you just find the inverse of this or multiply it by the partial derivative here, which is a Jacobian. So this is going to be another matrix. If x, let's say, is also of size 10, then that's a 3 by 10 matrix here. So recall that like this is how you actually get the Jacobian dy dx, right? And that's already perhaps going to be more efficient than the trying to differentiate the iterative solver. That's already a shortcut, right? And one thing or two things to note here is that you can basically, like if you try to define a rule for this or trying to compute the Jacobian, you're going to still need these partials, right? So that's a case where your rule can actually use further automatic differentiation to get these partials. So the rule can use automatic differentiation to get these partials and then use these partials together in such a way to define the rule efficiently, right? And so the rule is not fully defined just yet. We still need to have this here. And that here is something that you probably don't want to write by hand for every single function, but it's something that you can use automatic differentiation to get as well. But recall that we don't actually need the full Jacobian dy by dx, right? We only need this operator here, which takes a vector v of the same size as the output, and then returns us this Jacobian transposed by vector, which has the same size as the input. And so all we need to do is be able to multiply the Jacobian transposed by a vector v for an appropriately sized vector v, right? And so if we take the transpose of this, we end up with this expression here, and then if we multiply by v, then that's what we get, right? And now let's take a closer look at this thing here. And so if we have a vector on the right hand side, and then we have this here is a matrix, right? And so we're transposing the matrix and then inverting it and multiplying it by v, or alternatively you can actually look at this as just a simple a backslash b operation. So we're just solving a linear system of equation, right, where the a here is going to be the partial of f with respect to y transpose, and the b is going to be our vector v. And so if we have a way to get a backslash b or solve a linear system of equations here, then we get another vector at the end. And that's all we need to do. We don't actually need to compute the inverse of the matrix as long as we can solve this linear system of equations. And there are ways to solve a linear system of equations that are way more efficient than computing the inverse and multiplying by a vector. And so all we have here is a linear system solve and then another matrix vector product. So that's a matrix, and we're going to multiply it by the output from here, which is going to be another vector. And so a linear system solve and a matrix vector product is all you really need, and all the automatic differentiation package needs from your function in this case. And once again, when you're defining this rule using rrule, for example, using like chain rules core.rrule, the rrule function that I showed you earlier, you can use this automatic differentiation to get this, you can use automatic differentiation to get that, and then you can use them together to solve a linear system of equation here and then multiply by a matrix here. Right. And that's how you would define this rule using Julia or using chain rules, the JL. And this again is a shortcut. It's a nice way to propagate derivatives backwards way more efficiently than trying to differentiate the nonlinear system solver that you are using in the forward pass to evaluate y to begin with. And so the summary here is that first, you don't need to differentiate the nonlinear solver. Second, you don't need the full Jacobian. All you need is this operator here. And that's more efficient because, again, we don't need the full inverse. Here, we don't need this this expensive matrix multiplication here, which as x gets larger, this is going to be even more expensive, like way more expensive. So all we need to do is just be able to do one linear system solve and then one matrix vector product, right? And that scales much more kindly compared to this one here in terms of computational cost. So as x and y get larger, this is going to be more efficient than this one. Now, in some cases, in most cases, all you need is this, but in some cases, you actually need the full Jacobian. And in those cases, you have two options: either use this directly to get the full Jacobian, or if you have only this operator here, then you can also get the full Jacobian by actually a clever assignment of different vectors v. So if you choose v as the first column of the identity matrix, and then you multiply this out, or you apply this operator, then that's going to give you the first column of the Jacobian transpose, right? Which if you transpose it, it will give you the first row of the Jacobian. And so if you're choosing this to be the first column of the identity matrix, you get the first column of the Jacobian transpose, and then you can choose this to be the second column of the identity matrix to get the second column of the Jacobian transpose. And then you can assemble all these columns in a matrix form, and that gives you the full Jacobian transpose. Transpose that, and you have the full Jacobian, right? And so you can technically recover the Jacobian from this operator by just calling this operator a few times on all the basis functions or all the basis columns and vectors of the identity matrix, and that's a very, I guess, convenient way if you're trying to get the Jacobian. Now that's most likely going to be slower than directly doing this, and so this might actually be the better choice in this case. But hey, I mean, it's one way to do it, and if you only have this operator, then you can actually get the Jacobian using this method that I just discussed. So this is really everything I wanted to discuss in today's talk or video, and I'm going to leave you at the end with a few resources that you might be interested in. So there's this really nice course here for scientific programming that I was recently pointed to, and it covers automatic differentiation. There's a couple resources from the MIT math course on automatic differentiation. There's this paper here on abstract differentiation.jl, which me and some of my colleagues, we published recently, and actually it's going to be presented in the differential programming workshop or conference next week, which is like a NeurIPS workshop for differential programming. And so this is a really cool package that also gives an overview of differentiation in Julia, and this nice new package, abstract differentiation.jl, and how it makes life easier for developers and users of AD. And then we have more resources from the MIT course here, and even more resources there. And then we have the chain rules core documentation. So this is a very easy, like a very important reference to go to, especially if you're going to use chain rules core to define rules. This will teach you everything you need to know about the syntax of defining rules, and also some more about the math of automatic differentiation. And then at the end, we have our Julia Slack, in particular this AutoDiff channel, which is a very useful channel. A lot of people there, a lot of automatic differentiation experts hang out there who know way more about automatic differentiation than I do. And if you have questions, I often also check this channel out. So if you have questions, then feel free to join this channel and ask questions on that. And I or somebody more knowledgeable will probably be there to answer. So with that, I thank you for your time, and I hope that you learned something today.